Hi everybody, my name is Cyprien Todorov. I'm a postdoc at SDF in Brest, France. And today I am presenting a way of embedding time in Smalltalk. The overview of the presentation, I'll start with some context and the motivations. Then I'll introduce the logical time formalism that I am implementing. And I'll dive into the details of ClockSystem, that's the implementation of logical time in Smalltalk. I'll follow up with an example, and then I'll conclude and present some perspectives. So the context is simple. We have more and more parallel platforms with, for example, multi-cores, GPUs. In this case, we need parallel applications. And we can see that there are more and more parallel applications and more programming language support the parallelization. And also we have the distributed kind of applications that are spread over the internet, right? So as I said, most of the general purpose programming languages include support for specifying concurrency and sometimes for exploiting the parallelism of the underlying platform. The problem is that most of the time it is difficult to reason about these concurrent programs because the implementation is low level. These primitives are low level, and most of the time they lack some formal specifications, formal semantics. So if you want to analyze a multi-threaded application, you are doomed. To attack this problem, one solution is to use something that's called logical time. That's basically an abstraction of the physical time that we all know in terms of events. So basically we abstract the different things that happen in a physical world as events, and then we specify the relations in between these events. And since now we are thinking in terms of events, we don't care if these events they are directly time related or they are just some events that appear, for example, like when the temperature reached some 50 degrees, there is an event that pops up. It's not directly time related, so in that case we speak about multiform time. So this formalism introduced by Leslie Lamport enables to describe, to manipulate and to analyze the interactions, the communications, and the synchronizations in between parallel and concurrent and parallel entities. This formalism is used in hardware, embedded systems, and distributed systems. And there are some languages that made this formalism their core feature. These languages are Signal, Lust, STRL. And lately, the OMG MART specification introduced the clock constraint specification language as in the MART profile to specify time-related properties. So this clock constraint specification language was the source of inspiration for the work that I'm presenting. And basically, this the relation, it enables the description of relation between different events. This relation can be as a precedence, basically saying that I have this event that precedes this second event, or coincidence, saying that these two events have to happen at the same time. We have it has exclusion, basically saying that two events cannot happen at the same time. And there are some ways to generate new events from existing events. So basically, for example, we have two event sources. We can take the intersection of them and have a new event that is generated when both of our sources generate the event. The union and some filtering that I'll get into some more details in the next slide. And basically these kind of relations in between events can be used to enforce some semantics on the behaviors of the parallel processes, or to express some requirements that are to be checked later on a given implementation. So to get a better understanding of these relations, I'm presenting here coincidence relation in between two events, A and B, saying that each time the event A happens, B has to happen at the same time. So as we see in a chronogram, they are always at the same time. And the filtering expression that basically takes an always, in this case, takes an always event source. Basically, that's an event happening at each simulation time. And it filters it using this binary expression that's composed of offset and a period. The offset is, we can say that is like in an initialization sequence. In this case, the resulting event happens after two always events. Then I have one pause, again two events corresponding to these ones, two pauses corresponding to this 0 and this 1, and then I repeat that infinitely many times. So in order to implement this idea in Smalltalk, we can use this simple object model where we have our system that contains some relations. These relations can be parameterized with constants and variables. And the main idea is that the events, we call them clocks here. So we have these clocks that are related by the relations. And the relations, in ClockSystem, we have an automaton-based interpretation of this clock constraint specification language, so of the semantics of this language. So we are using automatons. And let's see, for example, one example. The strict precedence relation, which says that I have one event that should precede another. In terms of an automaton, we can represent it like this. Basically, we have the event A. Actually, it's not strict precedence, it's precedence. We have an event A happening, so basically the event B has to happen after, one step after the event A. So basically, then I have to have B, and then I can go back and, yeah, no. If I have an A, I go to this state. I can stay in this state with any amount of A and B's. If I get a B, I go back. If I get an A, I advance. And as you can see, this is an infinite automaton. So in order to represent it, we cannot enumerate all states of an infinite automaton. I use the simple trick to do it, basically a Smalltalk block, where I passed an integer specifying the state in which I am, and the block's responsibility is to return the outgoing transitions from the current state. So doing that, we can implement this precedence relation, much like this. Basically, if I'm in the first state, so if I'm in the first state, then I have just one outgoing relation. one outgoing transition. If I'm in any other state, I have 3 transitions, basically this one, and this one. Once I have these relations defined, I can just instantiate them. And I'm simply using Smalltalk messages to do that. And basically, we can have like different message synonyms. For example, for precedence, we can use precedes, or this sign, or comes after, or follows. And the user can specify whatever the domain, his domain terminology is, and use that for it. So a simple example, the synchronous data flow application. So basically what is synchronous data flow? We have different processes that will execute only when all input data is available, and upon execution, they'll produce instantaneously the output data and the given amount of tokens of output data. So basically, if we take this B process, it has to have 2 inputs in its input channel, and it will produce 2 outputs in one output channel, and yeah, it has to have another 2 inputs in this other input channel. So in standard code constraint specification language, you will specify that using a code similar to this one. So we have like a definition of an edge, like the connection in between 2 processes, 2 ports of processes. And basically, we have a source process, a target, clock. Basically, it's an event corresponding to the execution of a given process. The out production rate, the number of tokens that are found initially in the channel, and the number of inputs that are required by the consumer of the edge, or the target of the edge. And basically we'll say that the output is produced once this many times, output rate. So basically I have one output, one write event to the channel, and then I have to wait the time for n tokens to be written in the channel. The write in the channel happens before the read, delayed by initial tokens, basically saying that I have to write before reading, I have to write enough tokens before reading, being able to read. And basically the read is the opposite of the write, filtering the other way around. So the write says write, then I wait the tokens to be in the channel, and then at the same time the read will wait before and read at the end when all the tokens are in the channel. So in Smalltalk we'll have like the same 3 lines of code with some complications for specifying the period. Yeah, well, I'm using some array notation, some syntactic sugar here to specify like this power notation. The wait for, and yeah, basically the most important part is this one. That's basically saying I have a 0 for in minus 1 times, and then I follow with a 1. If we simulate this specification, we'll get one possible schedule amongst all possible schedules of our problem. So one possible schedule is to execute twice A, then execute once B, and then twice A and C at the same time, again A and C at the same time. So basically we'll get a periodic trace like this. We have the initialization phase of our SDF specification.
If you turn off Wi-Fi.
Okay. So then we can maybe interpret this periodic trace and get a simulation result for the given number of steps. I present here 21 steps. Also, we have implemented an exhaustive execution analysis that basically will export all the execution possibilities of the specification, and you can see here the result for our example. And basically, I emphasized the schedule that was presented earlier. And as you can see, there is one schedule amongst many others. In the case of a bigger application, we get something like this thing, and with one valid schedule that will be the X around. And yeah, in conclusion, we embedded a logical time formalism in Smalltalk with an extensible automaton-based formal kernel. We have a flexible DSL that uses message synonyms to relate to the user domain. There are different user scenarios, basically simulating a given formalism and interpreting the trace or model checking the specification, doing domain space exploration to understand better the problem at hand, and testing and monitoring of a given application. And in the case of concurrent Smalltalk application, I think testing and monitoring can be done by reflectively intercepting the generated events like variable access or method activations, and basically that will be your event sources, and then you'll say, yeah, I want this method to happen at the same time, or I don't care the order in which they happen. So then I can use mainly a coincidence, saying that whatever, if A happens before B or B before A is the same thing, so it's like they happen at the same time. If we're using an asynchronous communication formalism. Yeah, in the future I plan to do for dense time representation, basically instead of events having intervals in which things can happen. To integrate some mechanism, and yeah, this is like a more research-oriented point to investigate like how can we formalize the specifications in the case of dynamically evolving systems. In that case, our specification will have to evolve besides the system, and basically in terms of verification, model checking, I am not sure how that can be done. And yeah, another research topic will be to study the connection between this logical time formalism and different techniques of state space decomposition in the case of model checking. So yeah, thank you. If you have any other questions.
Any question?
Yeah, I have a question. Like, can you show us a slide? I don't know which number because it's important.
Yeah.
But the slides about the ClockSystem, because you've used this one. No, yeah, that one.
This one?
This one. So what does it mean, like equal?
It's the coincidence relation.
So what does it mean?
Is this equal here? This is not Smalltalk code. This is
Yeah,
like
I know.
mathematical code, right? So this equal. I didn't want to use mathematical equality because that might get confusing. Neither nor the identity. So basically equal. So I came up with equal. But anyway, you can, instead of equal, you can just say the keyword term like coincidence. That works also. And yeah, you can define your whatever you want.
So I have a question, like, about your future work. So I see, like, yeah, put the slide on future work.
Yeah.
Yeah, like testing, monitoring, concurrent Smalltalk application using the reflection, and to me that makes, sense, like really sense. The thing is, in most of the application we are defining is that each class, each object has an invariant.
Exactly.
And often, like, when there is a bug, meaning that this invariant has been broken somehow. But the thing is, I don't know when the invariant is broken, I don't know what the invariant is, but I'm pretty sure that there is an invariant, you know.
Yeah.
You are getting an object before adding some, and in the case of
Basically that's the idea. That's the main source of problems in the case of distributed systems and concurrent systems. You have basically a dependence of reading something after it was written. If that invariant is broken, you will get not the value that you wanted, for example. So looking at variable access will be very interesting. And also method activations to have a like higher level look at how the execution is proceeding. You remember that we are in a concurrent world where we have different threads of execution that are interleaved by the virtual machine, and we want to basically monitor or test that given assumptions are correct as they should. So yeah.
What I mean, many questions, but in the case of I'm dealing with pre-country is I usually have two threads, just the UI thread and the running thread. And can you particularize your approaches with just two threads? Because
it depends of
like how does it, can I use it right now?
yeah, we can try something. Yeah. I didn't get far enough with testing and monitoring part, but yeah, I have some very good ideas how to do it. So basically, the thing is that what will be most important is how you specify your event sources. So once you have these events, you will have to just say what are the relations, the relation in between these events. So saying that basically, I don't know, the read to this variable happens after the write, or I don't care about the order of these two events, or I don't know, I have to basically write twice or thrice in this array before reading it once, or before executing this X method once, I have to fill the array first, or I don't know. So yeah, I think it's
We should do lock.
Okay, so thank you.